Hi there! This is our fifth question in Centripetal Force, circular motion. Okay, let us read the question together. The figure shows a Ferris wheel which has a diameter of 140 meter and takes 2 minutes to complete a revolution. A person of mass 50 kilogram takes a ride on the Ferris wheel. Okay, then he asks us to find the angular velocity, the speed, the acceleration, the reaction of the person in the basket in two positions, A and B. So these are the common things. Okay, so information. Let's write down the information given. We have the diameter. This is the D. Takes 2 minutes to complete revolutions. Okay. Yeah, I write that down already. This is the mass, 50 kilogram. Find the angular velocity omega, the speed v, the acceleration, this centripetal acceleration actually, the reaction. Reaction is actually like the normal force, N1, N2. Okay, so all right. Now, information given here, we have the diameter. He say he make one revolution in 2 minute time. And actually, this is the period. Yeah, actually, this, if you understand, this one revolution is this is the period. Period is what? Period is the time taken to complete one circle. This you take 2 minutes to complete one circle. So this is the period lah. 2 minutes is the period lah. And we have the mass 50 kilogram. Okay, 50 kilogram. Find the angular velocity. Okay. So angular velocity is related to this one revolution 2 minutes. So how? We can write like that. We can write like that. He makes one revolution. He makes one revolutions in 2 minute time. Just divide. Revolution divide by minute. Yeah, revolution divide by minute. So how? On the top you just convert to radian because we know that omega is radian per second. What? Okay, is radian per second. Radian per second. So the top revolution you need to change to radian. We know that one turn is 2 pi radian. So multiply by 2 pi radian lah. You want to change to radian what? Okay, and then the top multiply by 2 pi radian. One revolution is 2 pi radian, and then 1 minute is 60 seconds. 1 minute is 60 seconds. So multiply 2 pi over 60. So what do you get? Just cut off all the these 2 and 2 can be cut off, and once we and what's the answer we get? We got pi over 60. We got pi over 60 radian per second. We got the answer. So pi over 60 is actually 0.052 radian per second. Okay, that's our omega. That's our omega. We got it. We got the omega. And then now, let's find the speed. Speed of the basket Ferris wheel. So speed of the basket, that means speed lah. V equal to R omega. That's our formula. So V equal to R omega. We R with diameter. So diameter, can find radius. Diameter just divide by 2. So our radius is 70 meter. Yeah. So 70 multiplied by omega just now is 0.052. 0.052. So the answer we get is 3.64 meter per second. That's our speed. 70 times 0. 3.64 meter per second. Now, okay, that's the speed. What's that? What else? Acceleration. Acceleration is the centripetal acceleration. Okay, so we have the V. So here actually you have two, yeah, you have two omega and also V. So if you like, you can use R omega square for AC. And also you have V already. So you also can use the formula V squared over R to find the AC. So see which one you want to use. Yeah, both same. So I use the V lah. Okay, V squared over R. So V squared over R. So just substitute. V I have 3.64. So just 3.64. Sorry, 3.64 square and divide by 70 radius. This is 6. This is 6. Okay, so answer 0.19 meter per second square. Yes, that's our centripetal acceleration. Now we done that centripetal acceleration. Now we want to find the reaction of basket at basket A and also the normal force at basket B. Two different positions. Now at basket A, let's look at basket A. Basket A, where is basket A? Oh, basket A is at the top. Let's draw the free body diagram first. It's very important for you to draw the free body diagram. So basket A, basket A, the person sitting in the basket, certainly it has the normal force. Why is blue? I want red. Okay, it has the normal force going up. So it's normal A lah. Put as normal A. Or just put as N1. Yeah? NA lah. Yeah, NA. And it has the weight downward. It has the weight downward. For basket B also, the person is sitting in the basket, so it has normal force going upward and the weight downward. That's it. Okay. So because the person is not upside down, the person is sitting on top of the chair, so the chair gives the normal force upward. For both positions, basket A and basket B, both persons are sitting on the chair. So both chair provides the normal force upward. Upward. Normal force upward. Both sitting on the chair. Okay? And the weight is downward. But one thing is, you must look at the centripetal acceleration, the center of the circle. Center is over here. You see or not? Come on. So give me the orange. Never mind. So the center is at here. So we have our so our center is at here. So at the basket A, our AC is downward. Our AC is downward because the center is at the bottom. Because the center is below A. Center is below A, so AC is downward. AC towards the center. Yeah, this is our center. And for basket B, the center is above. Center is above, so our AC is going up. Our AC is going up because AC towards the center, so AC upward. Okay, so now let's do the question. Just now, let's do the basket A first. Basket A is AC downward. Yeah, AC downward. That's correct. And this is our free body diagram. And the normal force upward, weight downward. So remember to write the positive and negative sign. Follow acceleration positive, opposite negative. That's it. So what we can say is the weight is positive, normal force is negative. Okay, just write that down, yeah? So the weight is positive, the normal force is negative. Okay? Alright. So this is equal to MAC. Yeah? MAC. So our then let's actually this is a centripetal force FC, yeah? Only the Y component. It has a Y component. So our NA is equal to this is W minus MAC lah. Or you can say it is a mg minus MAC. Alright. So what is our mass? Our mass is 50 kilogram. Yeah, 50. 50. Oh, we can actually factor this out. So mass is 50 And then G is 9.81. What else? Our G value 9.81. Yeah, our AC is what is our AC? I think we got the AC just now, isn't it? 0.19. 0.19. You don't need to use the V square over R anymore. We already got the AC. So just substitute the value of AC, 0.19. So this is 0.19. So calculate. We get 481 Newton. This is normal force at A. Sometimes normal force can also be written as reaction force. They are the same. Okay? They are the same. You can write as NA or RA. Reaction. Yeah? You can write this normal, or you can write this as reaction force. The same. They are the same. Yeah? Same thing like this one. Normal force. Also can write as RB. Okay, that's our normal force at A for the top. Now for the bottom. How about bottom? At the bottom, the AC is going upward because the center is above. So remember to put the positive negative sign. Follow acceleration positive, opposite negative. You see? Opposite than this one, you see? The positive negative sign. So, okay. So which force is positive? The normal force. The normal force is positive. The weight is negative. The weight is negative. Again, this is the centripetal force. Now, what's okay, let's rearrange. So normal force is equal to the weight plus MAC, which is mg plus MAC. So it's mass G plus AC. So what do you get? Mass is 50, G is 9.81, AC is 0.19, and this is 0.19. So our normal B is 500 Newton. That's our normal force. We can also write as RB. Okay, so what we can say is at the this is the answer. This at the top, this at the bottom. So what I can say is at the bottom, the normal force is bigger. The top, the normal force is smaller. What we can say is that at the bottom, what does it mean? Here it feels heavier. The person feels heavier, more attached to the seat. More attached to the seat. More attached to the seat. The seat. Yeah, more attached to the seat. It feels heavier, but at the top here, it feels lighter. The person feels like floating. Feels lighter, less attached to seat. Yeah, feels lighter. You see. So at the top, normally if the Ferris wheel turn too fast, the person normally thrown out from the top first, being thrown out from the top, because here the top feels lighter, more attached and less attached, but here it feels heavier. I mean more attached to the seat. So top is more dangerous than the bottom. Bottom is much safer. You feel more heavier, more attached to the seat. Here you feel like you are floating. If the thing is spinning too fast, if the Ferris wheel is spinning too fast, here you lose contact from the seat very easily. You lose contact from the seat very easily, being thrown out from the top easier. Yeah, here you fly away. Understand or not? Okay. So yeah, easily when you fly away, that means the normal force is 0. Normal force is 0. So I hope you enjoy the lesson. These are the things I just want to share with you. Okay. So I hope you enjoy the lesson. Stay tuned for the question 6 later on. Thank you. Bye.